Hi, you guys. It's Friday. I hope you are staying in. I hope you're staying well and staying healthy as always. We will finish off our section on vision today. So, our fourth lecture will focus on cortical aspects of vision. So, the striate cortex, the visual cortex, the pathways, and kind of use this as a bridge to higher cortical function in general, which will be our topic for the remainder of the course. So I'll let you read through the lecture objectives on your own. There's a little bit in Byrne and Levy related to this, but it's another lecture where I suggest you focus on the material that I've included in the slides. I won't read these out to you, but they're here for you once you've listened to the lecture and worked through the slides. These six numbered points should make sense, and these will be my expectations in terms of examinable material. All right, so we talked about the fovea and extrafoveal regions and the types of photoreceptors that are found in those two regions. And you'll recall that a receptive field, which we've defined on several occasions previously, but receptive field is the region of space that the region of the retina, right, the physical area of the retina that a given retinal ganglion cell is sensitive to. And a key point in the fovea, there's a much smaller ratio between photoreceptors and retinal ganglion cells. There's almost a 1-to-1 ratio. So the small receptive fields allow for very high resolution, but a relatively low sensitivity in terms of the number of photons that are required to activate the retinal ganglion cell. Elsewhere, outside of the fovea, there's a much higher ratio of photoreceptors to retinal ganglion cells, something like 15 to 45. One retinal ganglion cell to 15, 40, or 45, somewhere between 15 and 45 photoreceptors. And then our retinal ganglion cells, we can divide into two different subtypes. There's more, but for now, two. And we'll call them P cells and M cells. And they're differentiated based on where they project to in the thalamus. So in this pathway, the primary neurons are the retinal ganglion cells. Those are the ones that fire action potentials. And they project to the thalamus, specifically to the lateral geniculate nucleus of the thalamus. Within the LGN, there are layers. And so P cells are so named because they project to the parvocellular layers of the LGN. And those P cells they have small receptive fields. They exhibit cone opponency, which we talked about last time. So that should be a clue that they're important for color vision. Right? Color, form, and fine details is information that is projected via P cells, which are retinal ganglion cells that project to the parvocellular layers. So given these hints, color, form, fine details, where would you expect to find P cells? Foveal or extrafoveal regions? And hopefully, if we were in lecture, you would suggest that you might find these within foveal regions, and you would be correct. The M cells are retinal ganglion cells that carry different type of information, and they project to the magnocellular layers of the LGN. So they're more sensitive to luminescence, they have larger receptive fields, and they're important for contrast and movement. And if I were to ask you, where would you expect to find those? You might suggest, based on these hints, that those would be in extrafoveal regions, and again, you would be correct. So foveal and extrafoveal vision differ in these aspects, in resolution and in wavelength perception, right? Where here lambda is wavelength. So foveal is color, contains cones. The photoreceptors in foveal regions are cones, and they're important for color and high acuity vision. Extrafoveal is low acuity vision, right? Dim light, amount of luminescence, or photopic, right? You would refer to this high acuity color vision as scotopic vision, and dim light, low acuity vision as photopic vision. And those are the rods in the extrafoveal regions. All right, so visual information takes different pathways to the thalamus and the striate cortex depending on which region of the retina it falls on. So this figure is showing you a visual target, and then it's showing the visual target falling on the retina, and it's labeling different regions of the retina, and then it's showing the pathway that information takes to the thalamus depending on where on the retina the image falls. So you'll remember your basic physics. When an image falls on the retina, it is initially inverted, right? But then it'll be inverted again in the striate cortex, so you see something as it is, not as a mere image of itself. Okay, so let's just work through the basic anatomy on this slide. Right? So we have the temporal retina and we have the nasal retina. Right? Temporal retina, of course, closest to the temporal bone. Nasal retina closest to nasal bone, and the boundary between the two is the fovea. So if we're on the temporal side of the fovea, we're on the temporal retina, and if we're on the nasal side of the fovea, we're in the nasal retina. So there's a left temporal and left nasal and right nasal and right temporal shown on this slide. And you can see the inverted image, and then this is color coded for you, showing the pathway that information takes if it falls on the temporal retina versus the pathway that information takes to the thalamus if it falls on the nasal retina. Okay, so we'll build on that on coming slides. Okay, so in this case, we have an image that is very long, and it's long enough that it extends into the monocular field of view or monocular segments. So we'll look at the monocular segments on the next slide, but if something is in the monocular field of view, it is only falling on one retina, not both retinas. So this, the end, the tail of the arrow over here is so far over to the right that it will fall on the right nasal retina. However, it will not fall anywhere on the left retina. So something that's in the monocular field of view or is a monocular segment is only going to be seen by one eye. If you are going to see something in 3 dimensions, right, which is stereopsis, is seeing something in 3 dimensions, it must fall within the binocular field of view. So if something is in the binocular field of view, it means it's falling on both retinas, and you will see that image in 3 dimensions. This is your depth perception, because your brain relies on slightly different images from either eye. If it's only falling on one retina, there's no alternate image, so you're not going to see it in 3 dimensions. There won't be as much depth perception in your peripheral vision. Okay, so this would be the binocular segment. It's falling on where you have all the hash marks here. This is falling on both the left and the right retina, and that is something that would be seen in 3 dimensions with depth perception. And then there's a left and a right monocular segment here. And a good thing to jot down, the monocular segment is always falling on the nasal retina on the same side. So the right monocular segment here is falling on the images projected on the right nasal retina. Over here, the left monocular segment is falling on the left nasal retina. And I'm stressing that because we're going to talk about experiments in coming lectures where we're going to have images being flashed to the monocular field of view, and you need to be able to figure out where in the brain those images get. And so the fact that it's falling on the nasal retina is important because it's going to take a different pathway to the thalamus than if it were falling on the temporal retina. Okay, so I don't want to get ahead of myself, but I want to emphasize this to enough a degree that it sticks and you take it in. Okay, so we've talked about the boundary between the nasal and temporal retina. We've talked about where the temporal and nasal retinas are. I have stressed monocular and binocular, and I've talked about 3-dimensional vision and depth perception in the binocular segment versus monocular segments. So I think I've done everything I wanted to do with this slide. Let's move on and talk a little bit more about the monocular segment. So I stressed this already, but I'll stress it again. So you can see the lines I've put on this slide to show you, to highlight that something in the right monocular field of view is falling on the right nasal retina. It's inverted as always, okay, but it'll be inverted again in higher visual processing. So you would see the arrow here as facing right to left rather than the inverted vision. And similarly, the head of the arrow is in the left monocular field of view, and that's falling in an inverted fashion on the left nasal retina. Okay, so the monocular segment of the target is imaged only on the nasal retina of one eye, right, on the same side where that monocular field of view exists, left or right, respectively. And then the pathway of transmission for nasal and the nasal retina and temporal retina differs, and you can see that here, right? Information or images that fall on the temporal retina do not cross. They travel ipsilaterally to the ipsilateral lateral geniculate nucleus, right? So information on the right temporal retina would end up in the right LGN, whereas information that falls on the nasal retina crosses at the optic chiasm. Information that falls on the nasal retina is transmitted to the contralateral LGN and crosses at the optic chiasm. Okay, so information on the temporal retina stays ipsilateral. Information on the nasal retina crosses and ends up in the contralateral LGN. Okay, so that's what's meant by the pathway for transmission differs. Okay, we've talked about the optic disc. The optic disc is here, where all of the axons of the retinal ganglion cells converge, leave the eye. That is an anatomical blind spot. However, you don't perceive a blind spot because it's compensated for by higher level visual processing. So axons leave via the optic disc. They converge to become the optic nerve. Axons from nasal retinal ganglion cells cross. They're crossing right here at the optic chiasm, and temporal fibers remain uncrossed. Okay, so that means that images or objects that are imaged on the nasal retina end up in the contralateral visual cortex. Images or objects that are imaged on the nasal retina are represented in the opposite hemisphere, or the visual cortex in the opposite hemisphere. Okay, so contralateral processing for the nasal retina and ipsilateral processing for the temporal retina. Ultimately, all of the information is shared. Right? So all the information from the left visual field, whether it's monocular or binocular, will be conveyed to the opposite side of the brain via the corpus callosum. And you should remember from anatomy that the structure that allows sharing of information between the two hemispheres is the corpus callosum. And I'm stressing that here because we're going to talk about experiments where the corpus callosum is severed, and that can have impacts on a number of different aspects of higher brain function, one of them being vision. And a turning point in evolution, stereopsis and three-dimensional imaging, fine motor skills. A lot of evolutionary biologists suggest that binocular vision and the splitting of these pathways at the optic chiasm allowed for development of fine motor skills, but that's more of a side point, not something that we need to worry about in too much detail. All right, so a figure from another textbook, maybe just a little easier to see, a little bit of a different depiction of the binocular field of view here in the middle, and the monocular fields of view left and right, shown with the blue and red circles, and where on the retina this information is falling, right? Monocular falling only on the nasal retina on the respective side, here in the right nasal retina, and the idea that nasal information imaged on the nasal retina crosses at the optic chiasm and ends up in the contralateral LGN and the contralateral visual cortex. Whereas images that fall on the temporal retina do not cross. They end up in the ipsilateral LGN of the thalamus and the ipsilateral striate cortex. Okay, so I won't read through these summary points for you. I should have paraphrased all of these points on the last few slides and mentioned the optic disc and the LGN, and then the secondary neurons in this pathway would be thalamic neurons within the LGN. So retinal ganglion cells synapse onto thalamic neurons within the LGN, and those LGN neurons then project to the striate cortex, where we will find different types of cortical neurons responsible for different aspects of vision. Okay, so here we're looking at the anatomy of the lateral geniculate nucleus of the thalamus. Don't worry, well, this should just be review, right? These are our horizontal cells and our bipolar cells, so this is the anatomy of the retina. We've talked about either the ipsilateral or contralateral pathways crossing or not crossing at the optic chiasm, and those retinal ganglion cells projecting to the LGN. So here are the layers, the 6 layers. We've talked previously in the course about the 6-layered structure of the neocortex, and we can find the parvocellular layers and the magnocellular layers. In between, there's the coniocellular layers. Don't worry about those. They're very small. Less is known about them, but you do need to know that P cells of the retina, retinal ganglion cells that are P cells, project here to the parvocellular, and M cells, retinal ganglion cells that are M cells, project here to the magnocellular layers. So the magnocellular layers, this is a folded structure. That's layers 1 and 2, the magnocellular layers. And the coniocellular layers in between, coniocellular layers in between. And then the parvocellular layers are layers 3, 4, 5, and 6. So you can see they don't even number the coniocellular layers, so you don't need to worry about those. Magnocellular layers have center surround receptive fields. So we talked about retinal ganglion cells having center surround receptive fields, and so do neurons within the LGN. And so magnocellular layers, you should be easy. This is a low ball I'm throwing at you here. Magnocellular layers have center surround receptive fields and receive input from M cells. You'll recall that those are retinal ganglion cells, and you can go back a few slides to see the information, specific type of information they're carrying, related largely to movement and brightness. Those will be extrafoveal. And the parvocellular layers receiving input from the P cells, important for color and form. They also have center surround receptive fields. And we talked last time about cone-opponent responses, right? We had a green on center, red off surround type scenario. That would be a cone-opponent response. And those same types of responses have been recorded from LGN cells. So LGN cells are important for the initial processing of color vision. And so what do we mean by they have center surround receptive fields? So largely, it's a 1-to-1 ratio for a retinal ganglion cell and an LGN neuron. Okay, so one retinal ganglion cell projects to one LGN neuron. So you can just imagine that the LGN neuron, whether it's parvocellular or magnocellular, will have a receptive field that's similar to the retinal ganglion cell that's projecting to it. Okay, it'll be sensitive to in the same way, whether it's an on-center off-surround or whether it's a green on-center red off-surround. You could correctly refer to the receptive field of the thalamic neuron as mirroring or being similar to that of the retinal ganglion cell that projects to it. Okay, we'll come back to that a little later in lecture, but hopefully I can seed that idea now so that the slide makes sense. And then, so we said secondary neurons are found in the lateral geniculate nucleus, and those secondary neurons project to the primary visual cortex, primary visual area, V1, striate cortex. Those terms are all synonymous. And that's via the optic radiation, or sometimes referred to as the geniculostriate pathway, because it's projecting from the lateral geniculate nucleus to the striate cortex. V1, again, is layered. So here's another part of the course where the layers are important. And output, sorry, this shouldn't say LNG, that's a typo. That should say liquid natural gas. That would be a different lecture. In any case, this should say LGN for lateral geniculate nucleus. So you can just make a note that I typoed here. LGN output ends in layer 4. That's true for all thalamic output, right? So this is our secondary neurons projecting from the LGN to the striate cortex. And M cell, magnocellular input, ends in layer 4C alpha, and parvocellular input ends up in layer 4C beta. So all the visual information is going to layer 4, layer 4C, but alpha for M cells and beta for P cells. And then alternating 4C patches. So this is where we can start to talk about ocular dominance columns. So as we've seen elsewhere, within the cortex, neurons are often arranged in columns that run perpendicular to the surface of the cranium, the surface of the brain. And they're arranged in columns where neurons within that column are typically sensitive to the same type of information and receiving input from the same place, right? That's a good general rule. So ocular dominance columns just refers to columns of neurons within the visual cortex that are receiving input from either one eye or the other, right? So you might have one column and then another column next door, and one column is receiving input from the contralateral eye, and the other column is receiving input from the ipsilateral eye. So cortical neurons within a given ocular dominance column will be receiving input, right? They'll be dominated by input from one eye or the other, right? But any given ocular dominance column will be receiving input from a similar place, either the left eye or the right eye, but not both, and will typically be sensitive to the same type of information. So you wouldn't refer to a receptive field of a cortical neuron, you would correctly refer to its orientation selectivity or orientation sensitivity. And that's similar to a receptive field, but it's more complicated, and we'll come to that in a few slides. Okay. Retinal ganglion cells have receptive fields. LGN neurons have receptive fields. Striate cortex neurons found within ocular dominance columns have an orientation selectivity, similar to a receptive field, but more complicated because you've got to add up different receptive fields. There's no longer a one-to-one relationship here. We had a one-to-one relationship between the retinal ganglion cell projecting to an LGN neuron, and so we can say that the receptive field of the LGN neuron is going to mirror that or be similar to that of the retinal ganglion cell that projects to it. However, typically multiple LGN cells are going to project to one cortical cell. So if you're going to talk about the receptive field of the neuron, the cortical neuron in an ocular dominance column, you need to consider the receptive fields of all of the LGN cells that are projecting to it. So that makes the receptive field more complicated. So we're going to give it a new name, and we're going to call it orientation selectivity. Okay, we'll break that down in coming slides. From the visual cortex, there are other pathways, and those of you in the BNS program will be familiar with the dorsal stream and the ventral stream, which for our purposes we can simplify to the where pathway and the what pathway. So where is location, right? Recognizing where something is, and the ventral stream is important for identifying an object from your previous knowledge and memory. So there are a number of different visual areas aside from V1, but we're not going to talk about those. You'll learn more about those if you go on to take, I think it's BPK444 with, in any case, it's taught by Dr. Marigold, but we won't go into that that level here. V1 is the best studied. V1 is the one that we are concerned with. And in addition, from V1, there are these additional projections that are the dorsal and the ventral stream. Okay, so if you can simplify that for you, the dorsal pathway. Dorsal and ventral streams are shown down here. Dorsal is location, where something is in space, right? This is the where pathway. Motion, control of the eyes and the arms, especially if visual information is being used for a certain type of movement, reaching up to grab something, or catching a baseball, let's say. That would be a good example. And that pathway is V1, V2, and then on to V5 and V6. So yes, you should know that level of detail, but not more. And then the ventral pathway, form recognition. What is it? Right? This is your what pathway, and object representation. And that's also important for storage of long-term memory. Your knowledge of a dog and what a dog looks like, or a dog that you had when you were a child, or a dog that you have now, for example. And that's V1. V2 and V4 are the visual areas involved with the ventral pathway. So make sure you know those and the areas, and you can describe in the level of detail shown on these slides why the where and the what, or dorsal and ventral pathways, are important. All right, let's take a quick break, and then we'll come back and talk about receptive fields. So grab a coffee, make sure you've got adequate glucose levels. So I need your full attention for the receptive fields of the LGN cells and the orientation selectivities of the higher cortical neurons. So I'll get that up for you a little later today, and stay safe in the meantime. I'll talk to you soon.